Let's look at some example problems that use the normal distribution in a few different ways. These three examples that we're going to look at in this video are taken from your homework, so you don't have to redo those, but hopefully these will help you with the other ones as you work through. So this first example deals with circumferences of drive belts. And so we've got this machine that produces drive belts, and you can see the mean circumference is 292 centimeters, and there's a standard deviation of 3.3 centimeters, and we want to know. Notice the wording, it says the percentage of belts that have circumferences between 291.69 and 293.67 centimeters. Well, when we talk about percentage of belts, really we're saying what's the probability that any given belt will lie between those two values in its circumference. And so my recommendation to you for all these problems is to start by just drawing a quick normal distribution picture. Now, it doesn't have to be in any way accurate for this distribution. All normal distributions have similar shape. This is just to help us understand what we're looking for. And so I'm going to go ahead and do that. Wow, that's pretty good. All right, so there's my normal distribution. Pretty proud of myself there. Not proud of myself with the horizontal line. I could do better. And what we're going to do is label what we're looking for. And so, here's our mean, 292. And I see that 291.69 is a little bit less than the mean. I'm going to exaggerate this for the purposes of being able to see. So there's 291.69. Let's say 293.67 is further away from 292 than the lower value is. So we'll put that over here. And it says find the percentage of belts that have circumferences between those two. Well, I'm asking for the area under the probability density function between those two values. And that is my probability because recall that the area under the probability density curve is always 1, the entire area. So this is what we're looking for. And the question is, how do we get it, right? Technically, we want to integrate the normal curve from 291, point blah, 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 to 293. But we're not going to do that. We're not going to actually do that integration. The calculator can do it for us. But conceptually, this is what we're doing, right? So we'll just say f of x dx, where f of x is the normal curve, specific to this problem. But in the calculator, there's the normal distribution functions available to us. So let's bring that up. And we can say second distribution, find the normal distribution. Oh, wait. It was right there. And we don't want the PDF, we want the CDF. And pretty much in all cases, for us, we're going to want the CDF, the cumulative density function, because we're always talking about an interval between two values. So if we do that, the lower value is simply 291.69. The upper value is, of course, 293.67. The mean, of course, is 292. Standard deviation is 3.3. Could this get any easier? I think not. We hit enter. All right, 0.231, or about 23.1% chance of having those circumferences lie with it between those two values. I'll write the calculator notation here. Notice it's normal CDF, lower. Can I do this? It's lower, upper, mean, standard deviation. So lower, upper, here's the upper, mean, standard deviation. And so let's write that real quick. This is normal CDF, 291.69, 293.67, mean 292, standard deviation 3.3. And this is about 0.231 0.231, about 23.1%. That's pretty much your most basic normal problem. And you might say, well, why even draw the picture for that? Well, you might be right, but some problems are a little more complicated. So let's look at example 2. We have a test that it's been determined that the top 80% of the scores should be passing grades. Okay, and the mean test score is 45, standard deviation is 7. What's the lowest score a student can receive and still pass? This is a totally different kind of question because we're given the probability and we're asked to find a score. And the score is one of the x values in the distribution. And so it's kind of backwards from the previous problem. So again, let's begin with a normal distribution. I was so happy with that one, I wanted to copy it, but it's going to be too difficult. Good enough. All right. What are we looking for? I said we're looking for a score this time. But which score? 80% of the test takers should receive a passing grade. Well, when we talk about 80% receiving a passing grade, we mean the top 80%. And so I'm thinking that this area would represent the top 80%, and this area would represent the bottom 20%. What's the lowest score a student can receive? Well, we're talking about the bottom edge of that interval. That would be this. Okay, this is what we're looking for. This is our x value that is in question. How do we get this value, right? I can't do a normal CDF here because the first parameter in the normal CDF is the lower value, and I don't know the lower value, right? We have another function on the calculator called inverse normal, and it's, I believe, number 3 on your distribution menu. So inverse norm, and let's go to calculator again. You can see number 3, inverse norm. Inverse norm takes, as you can see, an area, the mean and the standard deviation, and it's going to tell you the x value. But wait a minute, what area are we talking about? I've labeled this 80%. How does inverse norm know that I want the top 80? Well, in fact, it doesn't. It's going to assume the area from the bottom end, which is actually negative infinity, right? Remember that normal distribution extends infinitely in both directions. So from negative infinity up to whatever this percent is going to give us that. So in reality, to get this x value, I care about this area, not this area for using the inverse norm function. So this area is 20%, and so we're going to put in a 20. The mean is 45. The standard deviation is 7. We paste that. Inverse norm, 20, 45, 7. Enter. Clearly, I've made a mistake. Oh, 20. Ha. The area is 0.2. It's not in percentage. It's in decimal form. Hit enter, and we get 39.1. So that means this x value is a 39.1. And let's break that down a little bit. So again, what I care about, let's label the area I care about as this. This is 20%. And so in my inverse norm, that is what we need to include because the inverse norm begins at negative infinity. So inverse norm, 0.2, 45 for the mean, 7 for the standard deviation, and this is about 39.1, okay? That's this value, right? Recall that the mean was, again, 45. And so we can see that's about, not quite a standard deviation below. Does that make sense? right? Recall that half of the values lie above the mean, so 50% is over here. If we go another standard deviation back, remember that 68% of values lie between -1 and 1 standard deviations from the mean, so we're about 1 standard deviation back, so this is about 34%, right? A little bit less than that. What's 34 plus 50? It's 84. Yeah, that seems to make sense. We're a little bit less than 1 standard deviation below the mean, and so this seems to make sense. And you want to try to make sense of your answers as usual, just to be sure that you're correct. And it's why it's important to know those basic facts about the normal, because you can really tell pretty quickly how whether or not you're right, or it seems right. There you go. So 39.1 is the lowest score. Now the question is, can you get partial points? You could answer this question that, okay, well, they need to get a 40 because 39 is too low. And, depending on the interpretation of that question. So there you go. Inverse norm, very important function to know. Okay. One more example. We've got a population of women, and their weights are normally distributed with a mean of 62.5 kilograms. And we know that 15% of them weigh at least 72 kilograms, meaning 72 or more. Find the standard deviation, right? So yet again, a different problem. Draw a picture to begin. Okay, so we've got a mean, 62.5. We're told something about 72. So put that over here. And what we're told is that 15% weigh 72 or more. So what that means is that this area is 15%. Now, how the heck do we find the standard deviation? If we look at the calculator functions that we've been using, well, they both require the standard deviation to give us values, right? The inverse norm gives us an x value, right? That's not what we're looking for. Normal CDF gives us a probability value, also not what we're looking for. And both of them require the standard deviation anyway, which is what we are looking for. So how do we approach this problem? How do we find the standard deviation when we don't have any calculator function to do that? Well, the way that we do it is we think back, do we have any relationships, of course, that include the standard deviation as one of the variables? And the answer to that is yes, we do. And this is why we care about right? This relationship between the value of x, a particular value of x, the mean, the standard deviation, and the z-score. So we call this a z-score for a distribution that's not the standard normal. So again, the z-score is the associated z for x, right? So if we were to convert our current normal distribution to the standard normal, what value of z would be associated with a given value of x? That's x's z-score. So let's take that formula and see how we can apply it in this problem. So I'm going to write that formula here. The z-score is equal to the value of x minus the mean over the standard deviation. And so I can see clearly that means that the standard deviation is x minus the mean over z. And the question then becomes, well, how do I find z, right? Well, remember, all we're saying here is that there's a standard normal distribution whose mean is 0 and whose standard deviation is 1, and that there's some z that's associated with 72 such that these percentages are the same. Hopefully that makes sense. This is sort of a key notion in dealing with the normal, right? There's some z-score in the standard normal that matches up with 72 such that the percentages are the same. And that's all we really care about, because what that means is the following. Remember, the z-score in a standard normal is the number of standard deviations away from the mean. Why? Because the standard deviation is 1 in the standard normal. So whatever z is, that's how many standard deviations we are from the mean. If z is equal to 1 and the standard deviation is 1, we're 1 standard deviation away from the mean. If z is 2 and the standard deviation is 1, we're 2 standard deviations away from the mean. If z is negative 1/2, then we are negative 1/2 standard deviations from the mean. So what that means is, whatever this z value is, it's the same number of standard deviations from 0 that 72 is from 62.5. And that's going to allow us to then use that to find the standard deviation in the other distribution. Okay, so how do we go about finding what z is? Well, now, if z is an x value in the standard normal, right? And I have a way of finding an x value in the standard normal. It's my inverse norm function. So what I want to do is inverse norm. Remember, for the inverse norm, we talk about an area first, so 0.15. And the mean is 0, and the standard deviation is 1. Now, your calculator has convenience that if you are using the standard normal, you can just leave that off. I don't think it'll let me here, though, because the way I do it, it asks for that menu. But if you were typing it out, it would let you do that. So 0.15, mean of 0, standard deviation of 1, and I got a negative value. What did I do wrong? Or why do I even know that I did something wrong? Oh, the z-score is negative 1. So I could plug in negative 1 here and get a standard deviation. That's wrong, though. And you should pick up on that, right? A negative 1 is over here, right? Somewhere. But I know 72 is on the other side of my mean. So what happened? Again, what happened here is that the area that I was given and paying attention to is not the area required by the inverse norm, right? The area required by the inverse norm is the area to the left of the value that you're looking for. And so the 0.15 is not the right answer, or excuse me, not the right area. We want 0.85, and that gives us the correct z-score. And you can notice, it's the opposite in sign, and that should make sense because 0.85 is the complement area, and so it's symmetrical. So the z value is 1.036-ish, right? So this is about, so z is about 1.036. And so the sigma, standard deviation, is going to be x minus mu. What's x? X is the 72, right? This is our x. Mu is 62.5. Z is 1.036. What is this saying? 1.036 is the number of standard deviations that x is from the mean, and that's why this converts us to a standard deviation. So we're talking about a distance from the mean divided by how many standard deviations that distance is from the mean. That tells us the standard deviation itself. Think about that. Make sure that makes sense to you. Okay, so (72) minus 62.5 x minus mu divided by the z-score, which we just found, 9.166. So this is about 9.166. 9.166 what? Kilograms. There you go. So again, make sure you know this formula and know how to use it. Make sure you know inverse norm and normal CDF, and you should be able to do the problems in this unit.